boundary value problems. Let's do it. And we're going to solve this boundary value problem. I picked a solution of an equation that I already know the solution to, but we're going to solve it a different way, and then we can compare. So the differential equation says that the second derivative of some function f plus the function equals 1, and then we have two boundary value conditions. So we know the function at 0 has to be 0, and at pi over 2 is 0, and that's just what I have, and it's no big deal. Okay, so that's my starting thing that I'm going to work with. So how do we solve a boundary value problem? The most famous boundary value problem that you're going to deal with is, Schrodinger's equation in one dimension or something like that. That's just an idea, but let's just do this in general, this boundary value problem. So the finite difference method, we're going to use Python, but we got some setup to do. So let's imagine that I have f and x, and I have discrete values for the function, and let's just pick these points right here. Right, but I do fix my values are fixed at these locations, and that's important. And these are separated by delta x, and they have some function f1, f2. They're finite values. Well, how can I find, if I call this fi, the ith element of f, right? So it's 0, 1, 2, 3, 4, 5, however you want to label them. They're all values. How do I find the derivative right there? Well, actually, I want to find, just because it'll be easier, we don't have the first derivative, we have second derivative. So to find the second derivative at this function, I want to write it as an expression of these values. So this is fi minus 1, this is fi plus 1, and I is my index. Well, let me find the slope right here at the halfway point. The slope at, I can write this as f prime of I minus 1/2, right? So I know that's dumb, but that's what it is. So the derivative is just the slope between those 2 points. So this is going to be equal to the final position, fi minus the initial fi minus 1 over delta x, right? Because that's my change in right there. Now I can find fi plus 1/2, f prime of I plus 1/2. It's the slope between these 2 points. So that's going to be fi plus 1 minus fi over delta x. Now how do I find the second derivative? Well, the second derivative at this point is going to be the change in this derivative minus the change in this derivative. So this is f prime, that's f prime. So I'm going to do f prime minus f prime. So let's write the second derivative as the following. F double prime at the point I is going to be f prime of I plus 1/2 minus f prime of I minus 1/2 over delta x, right? Because that is the distance from here to there is delta x. So I'm dividing by delta x. It's this slope minus that slope divided by the change. That's what that means. Well, I can put in my expression for f prime of I plus 1/2 and that too. So I get fi minus fi minus 1 over delta x minus fi plus 1 minus fi over delta x, and all of that over delta x. Right, so that's my... Oh, I got that backwards. Didn't I get that backwards? So it's this, f prime of I plus 1/2. Yeah, right there. Okay, so I can divide both sides by delta x, and I get fi double prime. I get negative fi. Let's put this one over here first, because that's what it should be. Wait, this is... Yeah, let's put this one first. So fi plus 1 minus fi. Now I have this term, minus fi plus fi minus 1, right, because it's minus and minus, and all of that over delta x squared, and then I can write this as fi plus 1 plus fi minus 1 minus 2 fi over delta x squared, right, because there's minus fi, there's two of them. And that's my expression for the second derivative as a finite difference, right, in terms of these points. Okay, let's go back to our differential equation, which is this. I'm going to write that as f double prime plus f equals 1. So f double prime I plus fi equals 1. That's my differential equation. And so if I know the values of these functions, I can plug them in and find the derivative and plug it into this equation. So what we're going to do, spoiler alert, is I'm going to have some guess function. I'm going to just pick values for these, and I'm going to use those to find actually define the value of the function, right, from the differential equation. And then that'll give me a better guess, and then I can do it again. So I can do a reiterative approach for this problem, but I'll keep these boundary values, the the same. I'll have those fixed. So if I use this right here, and I put in my my derivative, my second derivative into my differential equation, that is what I had. I'm going to use another piece of paper. I'm using a lot of paper because I'm writing big. So let's do that. Let's put this in fi plus 1. Right there. Fi plus 1 plus fi minus 1 minus 2 fi over delta x squared. That's fi double prime plus fi equals 1. Now I want to solve this for fi. Okay. So let's multiply both sides by delta x, and I'm going to subtract that. So I get fi plus 1 plus fi minus 1 minus 2 fi equals delta x squared times 1 minus fi. Right, so I multiply both sides by delta x squared, and then I, oh wait, that's wrong. Multiply both sides by delta x squared, and then I subtract that. So this is wrong. No, that's right. I subtracted that, then multiplied it. That's right. Delta x squared times 1 minus fi. Okay, now I can, I got a little bit of work to do. I shouldn't have really done this way. I want to solve for fi. Well, I can still use an old fi right there. I'm gonna have two different fi's, and I don't think this is the way I did it before, and it worked. And you could solve for fi, but I'm gonna solve this by actually just moving this over here, making it positive, moving that over there. I get 2 fi equals fi plus 1 plus fi minus 1, and then I get minus delta x squared 1 minus fi, and then I can divide both sides by 2. And then I do have fi on both sides, and that's fine. I'm going to use this. This will be my old value of fi, the function at that point, and that's going to be my new value. So what I'm going to do is I'm going to take my old values. I can find the value of the function next one, right? Imagine, go back on over here. Here are my boundary values. So those are set. So for this one, I will have an fi minus 1 because it's right there. I don't have it for here, but I don't want to change that one anyway. So for this one, I'm going to use this and this. For this one, I'm going to use this one and this one. And for this last one, I'm going to use those two. And again, that boundary value is not going to change. Now, in Python, we got a lot of work to do. We got to make this guess function. We got to make a list for my values. I'm going to have to make 2 lists for my function. I'm going to have to make an old list and a new list so that I can't change the list when I'm using the list. So I'm going to have an old list over here where fi plus 1, fi minus 1, and fi, and use that to find the new one. And then I'll go back through and then set my old one equal to my new one and do it again. Okay, let's just get started in Python. Like I said, there's a lot of stuff to do, and I forget how to do things, and that's what's important to kind of like refresh myself how to do this whole method. So here I am with Python. I'm going to give you the code. Don't worry about that. To make it bigger. Okay, I'm going to have a graph. Graph bigger. No, I want to make this bigger. Let's put it as x title is x, y title is y, and then a width, spell it right, of 400, height of 200, and then I have a curve to plot. F1 equals g curve, color equals color dot blue. Okay, so now I need to go through and make all my x values, right? So let's just go ahead and write our x values as a list. X is an empty list, and I'm going to start with my temporary x value that I can move along and fill in the list. That's what I'm going to do. So I'm going to start at x is 0, because that's one of my boundaries, right? I'm going from 0 to pi over 2. Now I do need to pick how many points I want to break this into. So let's call this NP, and I'm going to make it 10. 10 points, and we can change that later, but let's start with 10. So now I need the step size. dx equals, it's going to be pi over 2 times NP, right? Because I need to break that into, that's going to make me have step sizes of pi over 2 divided by 10. While xt is less than or equal to pi over 2, and again, pi over 2 is my boundary, so I'm moving up to that boundary. What I'm going to do is just add that value to my list and increase my value of x. So x equals x plus xt, and then xt equals xt plus dx. And then I'm going to print it, which you don't normally like to do that, but I'm going to print it just to make sure it's working. Okay, so there's my list of x values. You see it goes up to pi over 2. So that looks good. Okay, and there's only 10. Maybe we should save this. BVP, save, and there, BOP. I'll change the name of that. Okay. Now I need to make two lists, one for my old function and one for my new. I'm going to call these fold and fnew. And so what I want to do is to put in values for these so I can change. I need to start with a guess function. I'm just going to start with the function 0, 0, 0, 0. I'm going to put them all 0. And sometimes that won't work. And if it doesn't work, you could put in some other function. But if I do that, the boundary values are met, right? Because they're both at 0. So it should work. So let's go through the list of x values and use that to find an expression to add into these lists. I can't leave them empty, though, because I have to have something in there. I'm going to do this. For I in range length of x, right? So this will go through my list x and call each element the ith element, and I can use that expression I. You don't even really need that. Fold equals fold plus 0. Fnew equals fnew plus 0. So that's going to make two lists, fold and fnew, and we could print them. Let's just print the new one. They're the same thing. It should be all zeros. Yeah, 0, 0, zeros, just like I thought. Okay, so but now it is important that fold, fnew, and x all are lists of the same length. And remember, we're using lists instead of arrays because this is Web v Python. Web v Python does not have the numpy array, so we can't do that. Okay. Now, let's do this. What I want to do is to iterate over the function a certain number of times. So let's say n is 0 and n is 10. So I want to do 10 iterations. I'm going to do it 10 times. So while n is less than n. And so what do I want to do? The first thing I want to do is to calculate my new values of f, which I call fn. So for I in range 1 length of x minus 1. So I don't want to go through the whole list, right? Because the first one I can't do, the first element of the list, because I don't have a number before it. The last one on the list, I don't have a number after. I can't do those. So if I do for I in range 1, it starts at 1, not 0, and it goes to the length of x minus 1. So I'm not going to go through those two endpoints. I'm not going to change those. They're not going to come up. So I won't be those values. So I can type I minus 1. There's always an I minus 1. There's always an I plus 1. Now I'm just going to type in my differential equation, just like I derived over there. So this says fnew I, right? The ith element is going to be equal to, let's just put this as 0.5 times f old I plus 1, right? That's fi plus 1. I'm calling it f old, plus f old, which looks like fold, but it's actually f old, I minus 1, I'm looking at my thing, minus delta x squared times 1 minus f old I. So that is the differential equation. That's the differential equation I said. So that's going to go through and calculate new values of my function. Now, if I went back through the list again, I would just be using the same function to calculate this. It wouldn't change. So I need to take my old values and update them to my new values. Otherwise, like I said, one calculation would be the same as the last one. So to do that, I can say this. For I in range length of x, I always use length of x, you could use something else, f old I equals f new I. Now, you can't say f old equals f new. You can't, if you put those two lists equal to each other, they will be the same thing. And if you change one, it changes the other. So you have to go through item by item and make the items all equal. So that's what that does right there. Now that's it, right? I need to increase my value of n. N equals n plus 1. And I think that should do it. Now I'm not plotting anything. Okay, so I'm not going to see anything. Let's just print out. Let's print out f print f new. Let's just see if it changed after 10 times. And see if we have an error. That's what I'm seeing if my code has a mistake in it. Okay, so it does. There's something there. And the boundary values are met, 0, 0, and it only has 10 elements. Everything looks good. Okay, now what we want to do is to actually plot this and animate the function as it changes over time. So to do that, down here, what I want to do is to use an animated graph. If you don't remember how to make an animated graph, that's fine. I always forget too. The first thing I'm going to do is put a rate statement in there. This will slow down the loop so that it'll have time to plot the animated graph during each iteration instead of just doing it as fast as it can. The next thing I'm going to plot is I'm going to make a function called f1 data. It's an empty list. I'm sorry, it's an empty list. And I'm going to put all my values in there and then plot them at the same time. And that's how you make an animated graph. So down here, I could do it in the same loop, but I'm going to do it here for I in range length of x. I want to add my data points for all the functions I calculated into this list. I need to have that list emptied at the in the beginning of each loop, otherwise it doesn't work. So f1 data equals f1 data plus the xy coordinate that I want to plot. So that's going to be xi f new I. So there's my data point I'm plotting. Now I have all those. And then once I have all those, I can make a plot f1.data equals f1 data. Let's see if it works. You never know, it might not work. I should probably save. Did it save? Okay. Look, it worked. Okay, that's pretty nice. And again, I'm not done, right? I only ran it for 10 things. Let's run it for let's say 50, not that one. Let's run this for 50. And let's increase this a little bit faster, because no one can wait 5 seconds for that whole thing to run. It's slowing down and stopping. Maybe I should do it even more. Let's do 100. And let's run this at 40. It's kind of hard to tell it's changing or not. It does look like it's slowing down. Negative 0.4. Maybe do a little bit more. It was negative 0.4. I can't tell if it's changing or not, or if it just stops. Okay, it's good. It's converging to a solution. And you notice I only have 10 data points there. Okay, but let's go ahead and plot the solution. So switching over to the paper real quick. This solution to that differential equation that I have up here, the solution to this differential equation looks like this. And I'm not going to solve this. It's just what it is. Where did I put that? Oh, y as a function of x is 1 minus sine of x minus cosine of x. That's the solution. So let's just plot that solution and see if we get the same thing. So back to Python over here. I'm going to make a separate graph. So over here, let's make another curve. F2 equals G curve. Color equals color dot red. And once I have my x values in that list, I can use that to plot. So for I in range length of x. I'm going to calculate the function. So f analytical. I'm just calculating that as a number. It's, what did I just say? 1 minus sine of x, but I can use x of I, minus cosine x of I. Now I want to plot that. F2 dot plot. The x coordinate is going to be xi. The y coordinate is going to be fa. Yeah. Nailed it. Okay, let's increase the number of data points in there just to make it a little bit more interesting. Let's put this at 20. Let's see what happens if I change the number of points to 20. It looks a little bit smoother, obviously. And it's going to take longer to converge, I think. Yeah, so let's do this as 400, and let's increase this to 100. And there we go. Finite difference method. And again, this same thing can be used for situations where you cannot get an analytical solution. But you see it converges nicely. Very nice. Okay, I'm pretty happy. So there you go. I know it can get a little confusing thinking about this derivative as a finite difference, but that's what we have. So, okay. Link to the code down below. That's it.